Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are taking a deep dive into the very start of Unit 7, alternating current. We promise to make this really simple, completely exam safe, and hopefully remove any fear you might have about AC. We'll also see why it really dominates our world today.
Right. And this feels like a huge shift from everything we've done in circuit theory so far. I mean, for the past few chapters, everything was direct current. DC, the voltage was constant, current was steady.
Everything just flowed one way.
Exactly. Now everything changes with time. It feels so much more complex.
It is more complex in some ways, but it's also more elegant once you see the core idea. So before we get into any maths, let's start with a simple question, something from everyday life. You know that in India, the electric current in our homes, it actually reverses its direction of flow 50 times every single second.
50 times per second. That's 50 hertz, right?
50 hertz, yeah.
That's incredibly fast to even think about.
It is. So think about it. If the current that's pushing your fan or powering your light bulb is flipping back and forth, positive, zero, negative, back again, 50 times a second, why doesn't the light flicker? Why does the fan spin smoothly, continuously? Shouldn't it also be trying to reverse its direction?
That is actually very confusing. If the power source is constantly pushing and then pulling, how does the appliance give a continuous output? It just doesn't feel intuitive at all.
That is the beautiful, counterintuitive part of alternating current. In fact, if you listen very closely to certain appliances, maybe a large transformer or even an older phone charger, you might hear a low, steady hum. You know that sound.
Oh, yes, that soft buzzing sound.
That hum is not a mistake. It's not a defect. That sound is literally the sound of the 50 hertz oscillation. It's the magnetic fields inside reversing so fast that they make the metal coils physically vibrate.
Wow. So that sound is a direct sign of that rapid push-pull happening inside. That really connects the theory to something I can actually hear.
Precisely. And understanding how this rapid reversal can deliver continuous useful energy. That is the whole point of this chapter. Okay, so let's break down the core idea. At the most basic level, what is AC? Simply put, it's electric current that periodically reverses its direction. And this reversal isn't random. It follows a smooth, continuous sine wave pattern.
Which is the complete opposite of DC, which just flows in one constant path.
Exactly.
So if the direction is reversing 50 times a second, what are the electrons inside the wire actually doing? Are they running forward, then stopping, and then running all the way back?
That is an excellent question. And it gets to the most crucial difference between AC and DC. See, in DC, we learned that electrons slowly drift in one direction. Yeah. But in AC, there is no large-scale drift. The electrons just oscillate. They jiggle back and forth around their fixed positions.
So they're just shaking on the spot. They aren't actually going anywhere.
That's a perfect way to put it. They have zero net displacement after one full cycle. They end up right back where they started. What's actually being transferred over the long distance from the power plant to your home isn't the charge itself, it's the energy carried by the oscillating electromagnetic field.
Can you give me a way to visualize that, this idea of energy moving without the particles moving?
Yes. The water pipe analogy is perfect here. Think of DC as a steady flow of water in a pipe, from high pressure to low pressure. Simple.
Okay, that makes sense.
Now AC is like water sloshing back and forth in that same pipe. The individual water molecules don't really travel down the pipe. They just move a little forward, then a little back. But the energy of that sloshing motion, that wave, travels down the pipe very fast.
Ah, I see. And that wave of energy can still do work, like turn a water wheel at the end.
Exactly. The wheel will keep turning continuously. It doesn't care if the water is pushing it or pulling it right at that instant. The power flow is constant.
So the wave carries the power, not the particles. That explains how the fan keeps spinning.
Precisely. Now the big question is, why? Why did we choose this more complicated system? Why not just stick with simple DC? The answer is one word, and it's profoundly important. Transformers.
Right. This has to do with efficiency over long distances, doesn't it?
Absolutely. This is the single biggest reason AC won the war of the currents back in the day. You see, DC voltage is very difficult to change. But with AC, you can step the voltage up or down very, very easily and efficiently using a transformer.
And why is changing the voltage so important?
Remember Joule heating. Power lost as heat is given by P equals I squared R. Notice the I is squared.
So even a small current leads to a big energy loss. We need to keep the current I as low as possible for long-distance transmission.
Exactly. And since power equals voltage times current, or P equals V times I, if we want to send a huge amount of power, P, with a very small current, I, what must we do to the voltage V?
You have to make the voltage incredibly high.
Precisely. Transformers let us do that. We can generate power at a normal voltage, step it up to, say, 400,000 volts to send it across the country with minimal loss. And then, near your city, use another transformer to step it back down to a safe 230 volts for your home. DC just can't do this efficiently.
So the choice of AC was purely for economic and practical reasons of power delivery.
It was an engineering decision, yes. For the mental image, just picture that smooth sine wave. And the electrons are like tiny balls, just moving up and down on that wave, but never drifting forward. The wave itself is the energy.
Okay, so this voltage that was constant in all the previous chapters is now changing with time following this sine wave. How do we write that down mathematically?
Great question. That takes us to the formal technical language. Now that we have the feel for it, let's look at the exact definitions you need for the exam.
Okay, I have the definition from the source material right here. It says, voltage that varies like a sine function with time is called alternating voltage, X voltage, and the current driven by it is called the alternating current, AC.
Perfect. So the key is that sine function. It means the instantaneous voltage. The voltage at any time t is given by the equation Vt, V sin dat.
Okay, so V must be the peak voltage, the maximum push or pull the source can give.
Correct. It's also called the amplitude, and that co is the angular frequency. It's just a measure of how fast the oscillation is happening, and it's directly connected to the practical frequency Sheff and Hertz by the formula O/2P. For India, you must always remember, F is fixed at 50 Hertz.
Right.
Now, this leads to a really interesting problem, because the voltage is positive, then negative, positive, then negative. What happens if you try to take a simple average of the voltage over one full cycle?
The positive part would be exactly canceled out by the negative part, so the
Yeah.
average would be
It
0.
would be 0. And that's a huge paradox, isn't it? An average voltage of 0 can't be delivering any power, but our lights are on.
So a simple average is useless.
Completely useless. We need a different kind of average, an effective value that tells us how much work this AC voltage is actually doing.
An effective value, something that's equivalent to a DC voltage that would produce the same amount of heating.
Exactly. You've hit the nail on the head. That effective value is called the root mean square value, or RMS. And the name itself tells you exactly how it's calculated. You work backwards. Root mean square. First, you square the voltage. Vt becomes Vt. Squaring does two things. It makes all the negative values positive, solving our cancellation problem. And more importantly, power is related to VSO, so we are now looking at a quantity related to power.
Okay, square it to get rid of the negatives and think in terms of power.
Second, you take the mean or the average of that squared value over a full cycle. This gives you the average power. And third, you take the square root of that whole thing, just to get the units back to volts. And that's it. That's VRMS. Now, after you do all the calculus, a very simple answer comes out. VRO is simply the peak voltage, V, divided by the square root of 2.
So varions via...
Yes, and ETI are 2. And that factor, 1 over root 2, is about 0.707. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com.
Okay, I think I understand the logic of RMS. It's a power-aware average. But what does it mean practically? When they say the voltage in my house is 220 V, is that the RMS or the peak value?
That is a critical point. It is a universal convention. When we talk about an AC quantity, we always mean its RMS value unless specified otherwise. So 220 V is VES.
Oh, so what is the actual peak voltage that's hitting my appliances?
Let's calculate it. We know V is Ven's root 2. So that's 220 volts times about 1.414. It comes out to be approximately 311 volts.
Wait, what? So the wire is actually hitting a peak of 311 volts 50 times a second. That's so much higher than the 220 V number we always hear.
It is. And this is why the distinction is so important, not just for exams, but for engineering and safety. Your device operates on an effective 220 V, but its insulation must be strong enough to withstand a peak of 311 V. Let's quickly do one tiny worked example to lock this in. Suppose a voltage source is given by V equals 50 sin 100D.
Okay, so that's in the form via. The peak voltage V is clearly 50 volts.
Perfect. What is the angular frequency?
That would be 100 radians per second.
And from that, can you find the normal frequency? Yeah?
Yes, ubi so. So S is O divided by 2P. That's 100 divided by 2, which is 50 hertz. It matches the Indian standard.
Excellent. And now for the most important part, what is the effective voltage, the RMS value?
That would be VO divided by root 2, so 50 divided by roughly 1.414.
which comes out to be about 35.4 volts.
So a 35.4-volt DC battery would deliver the same power as this AC source that peaks at 50 volts.
You've got it. That confirms why we need RMS. And just one final connection before we move on. This sine wave isn't just a mathematical convenience. It naturally comes from the physics of generation, from what you studied in electromagnetic induction. Rotating a coil in a magnetic field, using Faraday's law, naturally produces a sinusoidal EMF. Now, let's talk about the silent killers. These are the common mistakes students make in exams. Misconception number 1 is the AC motion trap. The wrong idea is, in AC, electrons physically move backward. Students think this because they are used to the drift in DC.
Okay, so why is that wrong again?
Because the correct idea is that electrons only oscillate around a fixed point. They have zero net displacement. Just remember the hook. AC is oscillation, not reversal. The electrons just dance on the spot.
Right, they dance back and forth, but they don't actually travel anywhere. Got it.
Misconception number 2. The RMS average trap. The wrong idea is thinking that RMS is just the simple average of the positive values.
I can see why someone would think that. They know the total average is 0, so they might just try to average the absolute value.
Exactly, but that's a different quantity entirely. The correct idea is that RMS is the root mean square. It's a power-aware average, and it's calculated as V0 divided by root 2. Remember the hook. RMS equals root mean of squares. The name tells you the process.
Okay, not a simple average, it's a power average.
And the third one, the frequency trap. The wrong idea is that the AC frequency in India can vary between 50 and 60 hertz.
I've heard 60 hertz is used in America, so it's easy to get confused.
It is, but it's a critical fact to know. The correct idea is that the frequency is fixed by the infrastructure of the entire national grid. It is maintained at exactly 50 hertz. It doesn't fluctuate. The hook here is frequency is the grid's DNA. This is a fixed, constant value for us. All right, to make sure these concepts are locked in for your exam, let's use a few memory anchors. First, a simple mnemonic, AC, always changing. This immediately tells you it's time-varying and sinusoidal, the opposite of DC.
Okay, AC, always changing. Simple enough.
Second, a catchy phrase for the electron motion. Electrons dance back and forth, but the music plays forward.
I like that one. It really captures the idea that the energy flows even if the charges don't.
And third, a physical gesture. Whenever you're thinking about AC, just move your hand back and forth smoothly, like a wave, without moving it forward. This embodies that local oscillation.
I'm doing it now. It actually helps visualize it. Local oscillation, global energy transfer.
Fantastic. So let's summarize the 3 main factual points you need to remember. Point 1, definition. AC is current that periodically reverses direction, following a sinusoidal pattern, which we write as IT, is ISIN on OAPEB. Point 2, mechanism. Individual electrons only oscillate. They have no net displacement. The energy is what gets transmitted through the oscillating electromagnetic field. And point 3, RMS. The RMS value is the effective DC equivalent for power calculation. It's found by the formula V/2, and household voltage is always given in RMS. With this foundation, you are now fully prepared to tackle the rest of this unit. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROFSam, right?
Yes. PROFSAM.com. Study well, and we'll see you in the next deep dive.